Welcome in Cairo. Today we are going to continue our properties for light. Let's start by light interference. Here, the superposition of two light waves. The superposition of two light waves, they having the same amplitude, they having the same frequency, they having the same speed, but they form positions which are reinforcement of light, which are called the constructive interference of light, to form illuminated fringes. But another positions represented by destructive interference of light, zero amplitude, nil amplitude, it is dark fringes. We have here a comparison between constructive interference and destructive interference. Here, constructive interference, when here in the first wave and the second wave. Here we have two waves. When crest from the first source meets crest from the second source, the resultant wave as you see. Also, when trough from the first source meets a trough from the second source, so the resultant will be as you see. So, as you see here. So, here it is a maximum displacement. Here, the maximum displacement, upward or downward. So, when a crest from the first source meets a crest from the second source, or a trough from the first source meets a trough from the second source, it will produce, yes, constructive interference of light. So, we can see it as a bright fringe. But in destructive interference, when a crest from the first source meets a trough from the second source, or vice versa, trough from the first source meets a crest from the first source. So they cancel each other. Zero amplitude, dark fringe. And the path difference for constructive interference m lambda, but the path difference for destructive interference m plus half lambda. Okay, so that's for the comparison between constructive interference and destructive interference. What's about the Thomas-Young's experiment? We have here monochromatic source of light, cylindrical waves, double slit screen. We can receive it on observation screen, as you see. We can receive it on an observation screen. I'll repeat it again. Please, you have to concentrate well. We have concentrated here monochromatic source of light, cylindrical waves passes from one slit, from two slits. They act as two coherent sources of light. They can be received after superposition, after interference of light. In the Thomas-Young experiment, in the double slit experiment, we can see it as dark fringe, light fringe, dark fringe, light fringe, and so on. But the central fringe is always illuminated. The central fringe is always bright. Why? Because the path difference in this case equals zero. Here, application. What is the application of the double slit experiments? The application of double slit experiments, two applications. The first application to study the interference of light, as you see. Also, from the applications of Thomas-Young experiment or double slit experiment to calculate the wavelength of the monochromatic source of light. Here, the monochromatic source of light, we can calculate its wavelength by this experiment. Here, as you see, the distance between the two slits, in the double slit screen is called D, or is symboled by D. But the distance between the double slit screen and the observation screen, this distance is symboled by R. But the distance between two successive fringes, they are dark fringes or bright fringes. The distance between two successive fringes is R, or is delta Y. I repeat it again. The distance between the two slits is D. The distance between the double slit screen and the observation screen is R. The distance between two successive fringes is delta Y. Of course, wavelength lambda for the monochromatic source of light. That's for the Thomas-Young experiment. About the procedures, here A monochromatic source of light is used to emit light, as you see, with one wavelength, so the wavelength is only one value. At a suitable distance from the source, there is a screen with a rectangular slit to give out cylindrical waves, The double slit screen is adjusted to that so that the two slits S1 and S2 lie on the same wave fronts of the cylindrical wave. So the function of the two slits in the double slit screen, they act as two coherent sources of light. They act as the two slits. The function of the two slits in the Thomas-Young experiment, they act as two coherent sources of light that gives cylindrical waves. These cylindrical waves, they are in the same phase. Same phase means same velocity, same time, same displacement, same direction. When these waves are superposed on a third screen, which is called the observation screen, yes, an interference pattern is formed to form dark frames and illuminated frames. So, to calculate the distance between two successive frames, we can calculate the distance between two successive frames from the relation delta y equals lambda r over d. Delta y, the distance between two successive frames, equals lambda, the wavelength of the monochromatic source of light, times r, the distance between the double slit screen and the observation screen, divided d, the distance between the two slits. So, from this relation, we can conclude that as we increase the distance between the double slit screen and the observation screen, as we increase the distance between the double slit screen and the observation screen, as you see here, we can conclude that we can see a pattern, a clear pattern for the distance between the two successive frames. As r increases, delta y increases. As d decreases, the distance between two slits decreases, so the distance between two successive frames also increases. Also, if you use the red light, which has a long wavelength, so the distance between the two successive frames also increases. That's for Thomas-Young experiment. Example: in a double slit experiment, the distance between the slits is 0.0005 meter. The distance between the double slit and the observation screen is 0.75, and the distance between the two bright frames is 0.003 meter. Calculate the wavelength of the monochromatic light source. Of course, as you know, delta y equals lambda r over d. So, delta y, distance between two successive frames, yes, here 0.003, equals lambda, we want to calculate it, r, the distance between the double slit screen and the observation screen, it is 0.75 meter, divided d, the distance between the two slits, 0.0005. So lambda here equals 0.0005 times 0.003 divided 0.75. It will be 0.6 times 10 power negative 6 meter, or 6,000 angstrom. That's for this example. So at the end, I hope to understood our points for today, to understood light interference, Thomas-Young's experiments, and enjoy by our lesson for today. I hope also to join us in the next time. Thank you and goodbye.